Right, let's say we've got a 4 bundle conductors in an equilateral triangle with a radius of 1 centimeter for one conductor and for the bundles 20 centimeters. And let's say they are spaced apart 6 meters. So first of all, we are going to calculate ds for the small bundle. So that will be the 16th root of 0.7788 times 1 centimeter. That's 1 times 10 to the minus 2. There are 4 of them. And then we have 2r, which we have 8 of them. And then 2 square root 3r, which is 4. So with that, we get, oh, come on.
Mr. Leroux,
Yes.
can you please help us how to get that 2 square root 3?
All right, let's make it big. Remember, that line is like that, no? And this is 2r,
Okay.
and that is r. So this part here is going to be the square root 3. And because it's the whole length, it's 2 times.
Oh, okay.
Okay.
Okay, thanks. All right.
No, that's not right. Well, it can be. So that means it's 0.5732 centimeters, meters. So the radius is going to be half of that, 0.287. So now we've got a conductor like that and like that. The radius there is 0.287. And now it forms another bundle with 20 there. So now it is the 9th root of 0.7788 times 0.287. And there are 3 of them now. And then we've got 20 times 10 to the minus 2. How many? 2, 4, 6. That means it's fine. So that times 0.7788 times 3 power and 2e.
Sorry, sir, that power 6e, where does it come from?
There's that way and back, that way and back, that way and back. It's always from that one to that one, and from that one to that one.
Is
Same
that because of the linkage flux between the two conductors?
Yes,
or?
yes.
Okay.
So that gives us 4.4. So that is 0.447 meters. So that is ds of the bundle. Okay, and now we've got that. And then the equivalent is going to be the cube root of 20 times 10 minus 2 cube.
What is the mirror over the toothpaste? Over the with
And 20, so that equals 20 times 10 to the minus 2. And now L is equal to 2 times 10 to the power minus 7, then the equivalent of a ds bundle. That's 2 times 10 minus 7, then 20 times 10 minus 2 divided by 447.
Luna.
So that gives us 2,997 times 10 to the minus 7 henries per meter. Now, if we want to calculate the capacitance, then ds for the capacitor is now going to be the 9th root of 0,287 cubed times 20 times 10 to the minus 2 to the power of 6. Got that?
What about the roads? Where? So the loan or the
So that'll be 0.226. And C is equal to 2 pi epsilon 0 over the ln of E equivalent over ds of the cap. Right, so that is 2 pi times 4 pi times 10 minus 7 over the ln of 0.447 divided by 0.226. Okay, let's see.
That 4 pi exponent minus 7 is the permittivity of free space, or
Yeah, that's right. Times. I think I made a mistake somewhere. It is 8. So that gives us 1,158 times 10 minus 5 farads per meter. And that's basically one question that you can get. It depends on the type of bundle that we have.
So can I ask you a question?
Yeah.
On transmission line, when you calculate these GMR and GMDs, does the sagging of the conductors affect maybe the GMR? Because I believe probably the spacing will differ if they allow the conductors to sag.
Yeah, no, that depends on the weight of the wires, how far the towers are away from each other so that they don't sag too much.
Okay, sir.
All right.
Sir,
Yeah.
can you do? I see that you did single circuit. Can you do double circuit there?
No, why do you want to do that?
There are questions on double circuit.
Yeah, but forget about them. Let's not make life too hard.
Okay, super then.
At least I want you to pass, not fail.
Yeah. That will be great.
All right, anything else?
Do we on our test? Are we going to include the capacitance to earth, or it will only be?
It will be some same type of question like this.
Oh.
I might just give you a different configuration of the cables. Let's say it's going to be something like that. But that doesn't matter.
So those are two cables, space.
No, yeah, those are three conductors tied together so that you find D equivalent or DS of the bundle. And then you use the same principle again.
Okay.
Oh, like I said, I can give you this one, the flower. Or maybe on the corner of 4 of them, any configuration, it doesn't matter. So if I give you 4, it's going to be the same thing. First going to get the equivalent there, and then using that configuration to determine your equivalent diameter of the bundle. So if that is 20 centimeter, and that is 20 centimeter, and 20 and 20. First of all, what is that radius, that distance going to be?
I think it's
The square root of 800. And there's 2, and then there's 2 of them. You see?
Yeah.
Okay, any other question? But if you can do this one, you can do any one.
Yeah, you see on this one, I don't understand. Is it not that distance from, is it diagonal? That root 800, was it not supposed to be root 2 times the distance?
Yeah, but now you are given that. And that is 200, and that is 200. So what is that? It's a square root of that squared plus that squared.
Yeah.
Okay.
Yes. Okay.
All right. Any other question?
So the radius between the two conductors is always 2R.
Yes, that is when they are together. Like that. That is a R and that is a R. So that distance is 2R. And that distance is 2R, and that, and that. And this one is going to be 2 square root 3R.
All right. I'll have to revisit that chapter.
Okay, something else?
So what capacitance? Are you done with any example which you can do for us for capacitance?
That's basically this part here.
Done.
Yeah. So first of all, you calculate ds bundle for the capacitor, which is R cubed d cubed, or d to the power of 6, or whatever the case may be. And that's all that we need to calculate, is the capacitance of the line.
Oh, okay. No complications, ne? Besides capacitance of the line.
Yeah. So I'm going to give you the line and tell you, all right, I'll give you an example like this one here, and say determine the inductance of the capacitance of the line. That's it. And then when we get to transformers, I'm either going to give you a tap change or a phase shift. And then the same with the alternator. There you have to calculate P and Q, depending whether I say delta or E change. So those are the 4 combinations that you can get. So yeah, if you change delta, you're going to change P. If you change the excitation, you're going to change Q. And then again, I can say, all right, delta changed and E changed. What is that going to happen now? So you're just going to do the calculation.
All right, noted.
No catch. There's no catches at all. It's only a lack of knowledge on your part.
Yeah, maybe it's lack of knowledge.
No, I don't think if you know this stuff, you should be able to score good points. So anything else?
Say, in terms of that active power and reactive power, on, let's say, you're on transmission line, and then you have to represent it in terms of a phasor diagram.
Yeah.
How can you please draw it for us there?
Okay, let's say you've got a lagging power factor for the alternator. That's the angle phi. Now, if we've got resistance, it is always in parallel with E, with the current. That will be IR, and perpendicular to that will be IX.
No, I see. You see, this English is not okay. I wanted it on 4 Cartesian plane.
You want? 4 Cartesian plane. 4 Cartesian plane.
Yes. 4 Cartesian plane. 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 4 On a 4 Cartesian plane.
No, I can't hear you. Can you repeat that?
On a 4 Cartesian plane.
So you wanted this as a polar phasor diagram.
Yes.
Why?
Yes.
Why?
No, there's something which I did this Saturday at work, and then I couldn't
All right, let's say
draw that.
there is the voltage and there's the current. No? IR is going to be there. And IX is going to be perpendicular. There. And then we can calculate E, which will be somewhere there. So that is delta, that is phi. Now what we do for the string phasor diagram, we just grab this and put it on top there, and that one on top there, and then we've got E. Okay.
All right.
Just remember, civil, no? In an inductor, the voltage leads the current. Here we have a current. This thing is always rotating anti-clockwise. So therefore, this IX is the voltage. And that leads the current because it's turning that way. So therefore, this is in front of this.
So in this particular scenario, are you exporting? What are you exporting? Megavars or what?
That depends on what you calculate now. All right, so we say S is going to be V times the conjugate of IA. So in this case, let's say that is 30 degrees. And delta might be 8 degrees. Okay, doesn't matter. So then we have, let's say, 220. And the current is 40 amps at an angle of 30 degrees because I is 40, angle minus 30, it's lagging. Now, the conjugate, then the sign changes. So that'll be 8,800 angle 30. And then you will get P and Q. Both is positive, so therefore it's exporting both.
Okay, so if my reactive power is negative, I'm importing
Yes.
power, exporting active power.
Positive means, in this case, it's exporting. If it's negative, then it's importing.
So if I have two substations, I'm on the substation A, and then I'm reading both negative, it means that I'm importing.
Yeah, but that's going to be different. Some machine must export and the other one must import.
Okay.
So if we have, let's say, one station there, and a reactance there, then let's say this one is 220 angle 10, and this is 220 angle 0. Remember, the current always flows from the positive one or from the leading machine to the lagging machine. So here we will have E is going to be 220 plus, let's say, 40 at an angle of whatever, minus 30 times the resistance or the reactance of the machine. And from that, you will see that the one machine is exporting power or reactive power and the other one is receiving it. Or both is exporting a certain amount of reactive power because this line is taking them all. If you go back to engineering 3, you've done a lot of those problems there.
That was 2010, sir.
Too bad. If you do your advanced diploma or BTech, you must know everything from your diploma. Okay, we've got 3 minutes. Do you want another 40 or can we finish this?
Let's finish this.